Okay, so here we are with white blood cells. This is also from Module 2, Chapter 6. We just finished, or hopefully you just finished, watching red blood cells. There's a little bit of background information in red blood cells that will help you with this section for white blood cells. So let's go on into this. All right, you might remember this diagram from the red blood cells chapter, which again shows the differentiation of stem cells from the bone marrow into the different types of blood cells. Okay. Blood cells do differentiate into several different types of white blood cells, and so we're obviously not going to be able to cover in extreme depth each type, but we will be able to do an overview. Okay, so remember again that we had this stem cell which comes from bone marrow. Okay, this then produces either megakaryoblast, which create platelets, or way over here on this end, the erythroblasts, which create erythrocytes, or the red blood cells, which is what we just did. Or they create one of the three white blood cell stem cells. And those white blood cell stem cells are called lymphoblasts, monoblasts, and myeloblasts. Okay. Then if you notice, these are going to further differentiate into 5 different types of mature white blood cells. So when we talk about a mature blood cell, we're really looking at these final stages. Okay, from the erythrocyte, lymphocyte, monocyte, neutrophil, eosinophil, and basophil. This for the erythroblasts, lymphoblasts, monoblasts, myeloblasts. This is this intermediate version between the original stem cell and the finished mature blood cell. So a lot of times when you're talking about blood, you'll talk about they mature into either this, or that. So we saw that some in the red blood cells, and it will come up again here. So let's take a look at this for a minute. This is actually a really handy chart to help keep things kind of just in line. Lymphoblasts are going to differentiate into lymphocytes. This is cool because LYMPHO, the lympho part, is going to translate from lymphoblast to the lymphocyte. So it helps to remember. We'll go into each of these types in a little bit more detail, but lymphocytes are active in a specific immunity, which has to do with targeting specific pathogens. Then we have our monoblasts, which become monocytes. So again, the mono carries over, and these are going to become phagocytes. And phagocytes are things like the macrophages that we looked at or heard discussed in the red blood cell part. They engulf and break down disease cells or pathogens. Now we got to get over here to the myeloblasts. This is where the name similarity stops. Myeloblasts can differentiate into 3 different types of white blood cells: neutrophil, eosinophil, and basophil. The good thing about this one is when you see the PHIL in these terms, remember that PHIL goes back to the myeloblasts, okay? Because if you see a lymphocyte or a monocyte, these cyte, C-Y-T-E, which means cell, these are going to be replaced with blast. So lymphocyte comes from a lymphoblast, monocyte, monoblast, and then the fill ones come from the myeloblast. Okay? All right, so white blood cells. White blood cells are also called leukocytes. I'm going to pick up the wrong pen. I think I did pick up the wrong pen. Okay, they're called leukocytes. Leukocytes, the white blood cells, are particularly important in defense against disease. They're a part of our immune system. Immunity. Okay. Remember again that just like red blood cells, these are going to arise from stem cells that are created in the bone marrow. Okay. They have something called a colony stimulating factor. Colony in this case, well, I guess it's what you think of with the word in general. It's a group of individuals, right? Smallish, but still an organized group of individuals. And so that's what white blood cells are. They're a colony, and they're organized. And they have these stimulating factors, which means that one type of white blood cell will alert another type of white blood cell, and that other type of white blood cell will go get recruitment. We'll go get, that's not what I meant. We'll go get backup, okay? And pretty soon, you know, backup is getting more backup, and you've got this small little army now that's coming in to fight the source of this infection. And so colony stimulating factor just means that the red blood or the white blood cells have the ability to stimulate more of their kind coming, as well as more of other types of white blood cells coming. This is a really important part of the immune system. It's what allows it to work together against so many different types of pathogens from so many different sources. This colony stimulating factor is also going to be part of what regulates the growth of each type of white blood cell. It kind of helps to determine how many of each type are required. So to put it, probably oversimplify it, basically the colony stimulating factor is kind of monitoring what's happening in the immune system. When there's a specific pathogen that enters the body, there are specific types of white blood cells that are going to be used to fight that pathogen. So once that's been determined and the white blood cell has sent back the message of essentially, hey, this is the pathogen we're dealing with, the colony stimulating factor will be like, all right, then I need more of these types of white blood cells to go fight it. Okay. So just like the erythropoietin and the EPO is what controlled the production of red blood cells, the colony stimulating factor is what is going to stimulate the production of more white blood cells. So remember that this not only regulates the growth in general, but also the type of white blood cell. Did I say red blood cell again? I mean white blood cell. Okay. And again, the type, because different types of white blood cells attack different types of pathogens. All right. So let's go over some basics for how white blood cells fight infection. We'll go over this a little bit more when we come to the immune system, but we need these basics on white blood cells before we can talk about immunity in any depth. Sure, that's some frame for you. Okay. All right, so here's some examples of how white blood cells fight infection. Examples. Okay. So, they can fight an infection through a process called phagocytosis. And again, this is cells eating. Okay. We also discussed this very briefly in cell transport across membranes when they're bringing solids in. But phagocytosis is also an extremely important part of immunity. Okay, what happens is these specialized cells, because not all blood cells can phagocytize, invaders, but certain types of white blood cells are actually going to engulf. I'm going to actually just put invader because we can be dealing with viruses, we can be dealing with bacteria, we can be dealing with parasites, cancer cells, rogue proteins, toxins. I mean, the list of what our body can and does encounter is massive, to be honest. So I'm going to put invader because it kind of just says everything that doesn't belong here. Okay. So let's say that we have, here comes my drawing skills. You guys love when I draw, right? I actually don't draw a ton in this class, but let's say that this is the invader. And I don't know why I used that voice, but apparently I felt like he was a pirate. Arr. Okay, so there's our invader. And then we have a larger, because they are larger cellular size-wise, a larger phagocytic cell. This phagocytic cell does this, okay? It's going to create this indentation and engulf this parasite, okay, or this invader. And so basically, as this comes in contact with the cell membrane, this is going to encircle it and close off, okay? So that then what you have is our white blood cell now that has completely phagocytized our pirate invader, okay? There it is. And it's going to get sent to a lysosome. Remember that lysosomes are the sac of digestive enzymes within a cell. And so phagocytic white blood cells have lysosomes. That's my lysosome. There you go. Not creative with that one. Okay. And the invader is going to be sent to the lysosome because a part of the membrane is going to encircle this, drag it up here, merge with the lysosomal membrane, and release the invader into the lysosome, at which point the lysosome will do what a lysosome does, and it's going to digest the pathogen. Okay, it's going to destroy it. Okay. All right, so now that that's happened, we're going to talk about antibodies. I guess a little bit before I just dive into antibodies, I want to talk about what happens after a pathogen, an invader, is destroyed by a lysosome inside of a phagocytic white blood cell. The lysosome breaks this down, it takes it apart, and then it's going to take the identifying characteristic, which is usually like a protein complex or a sugar complex. It's going to take the identifying characteristic of the invader, and it's going to send a copy out to be displayed on the cell surface. Okay? Because then this is going to act as like a messenger for the other white blood cells. You're going to be like, dude, that's the enemy. When you see one, kill one. Okay? So that's kind of what happens when we've got antibodies. Antibodies are proteins. These proteins are everywhere in our bodies. And they bind to an antigen. So antigen is bad. And an antibody is usually good. The antigen is actually the specific component of the invader that causes the disease, right? So it's often this thing right here that's getting displayed. Okay? So we've got antibodies that bind to these antigens. An antigen overall is just defined as any substance that triggers an immune response. And guys, I'm not going to say necessarily just foreign substance, because in autoimmune disorders, antibodies are created against the body's own healthy cells. So I'm just going to say any substance that produces an immune response. Okay, so these antibodies can act as a trigger for phagocytosis. Again, the immune system we're going to get into a little bit more because there's different pathways through which this can happen. Sometimes antibodies that already exist because of a prior exposure, either through a vaccination or previous illness, sometimes the antibody recognizes the pathogen first and then releases the chemical that triggers phagocytosis. Good grief. That triggers, I can't think, cells that will come and phagocytize it, okay? And other times the phagocytosis part happens first and the antibody attaches to the antigen and then creates a larger phagocytic event. We'll get into that a little bit more when we talk about the immune system, okay? I'm gonna leave this here for a second so you can make sure you get all the notes. Okay, let's keep going. Okay, so now we're going to talk about some of the differences between these white blood cells that we talked about. And we are going to probably get into some more differentiation because even within the differentiated stem cells of the white blood cells, we are going to be dealing with, sorry, trying to make sure you can see. Even within that, we're going to be dealing with more further differentiation. Okay. All right. So let's start with neutrophils. Neutrophils are a type of white blood cell called granulocytes, which means that they're like these little granules in the cytoplasm. Okay. All right. So some of the characteristics of these neutrophils are the first responder to a bacterial infection, because remember I told you that different types of white blood cells respond to different types of invaders. So for bacteria, neutrophils are the first line of attack, or yeah. Respond. Neutrophils tend to phagocytize anything that they don't recognize and don't like. Okay, so anything that seems to be a foreign bacterial invader, the neutrophils are going to be all up on top of. We do have bacteria that lives on and in us constantly. Those types of bacteria that are part of our own ecosystem, if you will, in our bodies, don't usually get attacked unless they turn into a massive overgrowth, which can happen. Like we have E. coli in our gut all the time, but if we're introduced to E. coli that comes from another source that's not native to our bodies, we can still end up with a really bad E. coli infection. So neutrophils often, generally when things are working properly, can tell if this is foreign to the body or if it's a bacteria that we have a symbiotic relationship with. So the gross and awesome kind of cool thing about neutrophils is that when you see pus, like in a wound that's gotten infected, it's actually mostly made up of neutrophils. Okay? Hang on, I always spell that wrong. It's not a cat, it's pus. Mostly neutrophils. Okay. All right. And again, these guys are going to anything I'm going to put like in quotes here. Anything that they're like, hey, I don't think you belong here. Haven't seen you around before, so you're out. All right. These are actually the most abundant type of white blood cell. A couple of other factors I'm just going to include here. Well, it goes along with this really. So pus is mostly neutrophils. We know that pus is kind of a yellowish, grayish, brownish color. That's because when neutrophils die, they kind of turn yellowish. Okay. Also, shoot, where was the part I was going to tell you? Oh, there it is. That's right. Okay, there it is. So, fragmented nucleus. So instead of it being like the nucleus that we see in animal cells, like the classic animal cell, neutrophils have a fragmented nucleus, which is why you can see the staining pattern of the nucleus here, kind of all of this. Okay? And these characteristics are generally easy to view beneath a microscope if you use the proper stain. Usually either using a red acid type dye or a blue basic type dye. Neutrophils will actually stain with either because they're kind of neutral pH wise, so they will take whatever. And the nucleus especially will stain, and you can see this unusual pattern or unusual composition of this nucleus. Okay, let's talk about eosinophils. I've heard this pronounced another way, but at the moment I can't think about how else it's pronounced, so I'm going to pronounce it the way I usually hear it pronounced. Anyway, these are kind of cool because their job, I'm going to move this up a bit, their job is actually to protect against and attack parasitic organisms, okay? Large parasitic organisms like parasitic worms. L-A-R, I can spell, I can't spell. Not when I have to do it in front of people. Okay. So their response happens because of the inflammation in the tissues. The tissues are creating an inflammatory response because of the pathogen, in this case the parasite actually, that has invaded its space and is secreting chemicals that are toxic to the cells. So the cells become inflamed, and it's this inflammation that actually triggers this white blood cell to come in and start the attack. And again, they are going to phagocytize these parasites, process the proteins, and then it can be displayed. The proteins can be displayed so that they can be recognized, and any other parasites that may be present in the system with the same protein composition will also be destroyed. Parasitic proteins. Okay, so these guys tend to stain a red color when you stain them. It's something you have to do in a lab. And they have a bilobed nucleus. That doesn't look like bibbed. Let me try this again. Bilobed. Let me stretch out my letters. Bilobed nucleus. Okay, which you can see here. And again, which you can also see stained under a microscope. Okay, now let's talk about basophils. Make sure that this is still where you can see it. Okay, let's talk about basophils. Basophils are part of the allergy response in our bodies. And allergy, I mean like, well, anything you're allergic to, whether it's a peanut allergy or pollen in the air, it's basophils that are active. They actually trigger the release of something called histamines, which you may be familiar with because we've talked about in class, at least I think we have. We've talked about antihistamines, which block the production of histamine. Because histamines are actually what's responsible for the miserable responses our bodies have to allergens, and just, seasonal rhino type allergies. Rhino meaning nose. Now I'm picturing a rhinoceros. Anyway, you get like the cold symptoms kind of where you've got like a runny nose and sneezing and your eyes sting or water and your throat may burn. That's actually due to this histamine reaction that's caused by basophils. Okay. So these guys are the ones that come in to respond to allergies by triggering the release of histamines. Jeez, release of histamines. Okay. All right, so what happens when we have this reaction? First off, we have a dilation of the blood vessels. Okay. This increases the blood flow to wherever the allergy reaction is taking place. We need to increase the blood flow because we need a lot of white blood cells to hurry to the scene to start shutting down the problem, right? So we're going to increase blood flow, and we're going to increase white blood cells to the site. Okay? All right. The crazy thing about basophils and their triggering of histamine is that histamines can actually lead to fatal reactions because the body gets overly excited to deal with this allergy. Okay, so we can actually end up with swelling and inflammation due to the increase of white blood cells at some of these sites, and it can constrict our air passageways. Now the thing is, they're kind of supposed to, because a lot of allergies come in through our air passageways. And so when we have this constriction take place, it's supposed to prevent further exposure. Right? That's why you can feel like your chest is kind of tight. It's why you have the sneezing and the runny nose, because they're trying to like rid the body of this allergen. Right? Trying to get rid of it the way it came in, usually through the nose. However, this can get out of control, and in severe allergic reactions, you can have something called anaphylactic shock, which is basically where the allergy response of the body, in an attempt to destroy the allergen, actually severely shuts down the passageways and stops breathing. So, like, your throat will swell closed, so that air no longer can make it down the trachea. This is obviously severe. People that have truly severe allergies to a food or a medicine or a specific type of dander usually carry an EpiPen, because that has a chemical in it that is going to help reverse the histamine reaction. I believe it's epinephrine is what those usually have. And that will be life-saving. That's usually what is administered in the hospital. If you go into the hospital in an emergency situation with a severe anaphylactic reaction to an allergen, usually we'll give you epinephrine and it reverses this pathway, this problem. Basophils can also be responsible for asthma attacks. Oops. For those that have asthma or asthmatic tendencies. I had a friend growing up. She was my best friend in the whole world. And she had asthma really severely as a kid. And I remember that one day she came to my house, and we did have a cat, but as long as the cat was never in my room, she did good, because a cat was one of the things that could flare up her asthma. But of all things, we started telling stories one night, and we were laughing so hard, and I swear we were like in 4th grade, so I don't know, whatever was hilarious to an 8 or 9-year-old. And she had a crazy asthma attack, and they ended up having to take her to the hospital. It was seriously traumatizing. But that's just another side story. You know how I tell you side stories from my life? Anywho, so it causes this constriction of airways, and so if people have an allergy reaction, like my friend probably did to the cat, and then the laughing made it worse, the allergy reaction constricts the passageways even further, and for asthma sufferers, that almost closes down the airways completely in the lungs. Okay, moving on. Guys, I was trying so hard to make this one short, but I love immune system science so much that I'm like talking more than I thought. I will try to cut it down. All right, let's move on to monocytes. Monocytes are non-granular or agranular, hence agranulocytes. Okay, so remember that the fills that we just looked at, these guys were granulocytes. The next ones we're going to look at are agranulocytes. Okay, so one of these is a monocyte. Here's that word mature. A monocyte is going to be a white blood cell that will mature into a macrophage. We talked about macrophages with the red blood cells because macrophages are the ones that break down red blood cells when the red blood cell's life cycle is over. Macro is big. Phage means to eat or ingest. So, you know, I guess it directly can be called a big eater, but mostly what it means is it can also eat big things. So the translation kind of works both ways. These are the largest white blood cell, which makes sense because they've got to ingest a lot of stuff, right? I actually kind of wrote this backwards because it's the macrophages that are the largest white blood cells, and they come from monocytes. Okay, so the process of maturing for the macrophage actually doesn't complete until they leave the bone marrow and get into the tissues. That's when they finish this maturation process. And this is important too because white blood cells often have different locations for where they reach maturity. It's not always in the marrow. Okay, so again, these guys are going to destroy pathogens through phagocytosis, through eating them. Okay. They have a signal, if you will, that calls to other immune cells in the area to help fight off the infection. So it will locate a pathogen, locate an invader, phagocytize it, break it down in the lysosome, display its information on the surface, and this prompts the other white blood cells that are in the immediate vicinity to begin the hunt as well. And this in turn is going to send other signals back to the colony. Totally went blank on that. It's going to send it back, to the colony. No, send it back for the colony stimulating factor, so that more of the correct type of white blood cell will then be produced to assist in the destruction. Okay. So I'm going to use the word summon. It sounds so powerful, doesn't it? Summon other immune cells. Thou shalt come and fight pathogens with me. Summon other immune cells. Obviously to fight off the infection, or to fight off, I'm going to put invasion because it's okay, a little more general. Okay, so then we have lymphocytes. These guys are responsible for targeted immunity against specific pathogens. And again, we'll get into these in a little bit more detail with the immune system, but lymphocytes respond to, so we've got macrophages, right? And they're going to find a pathogen, destroy it, digest it, and then break down the proteins to be like, okay, this is what we're looking for, is this part. This is the antigen. This is the disease-causing part. When the colony stimulating factor begins to signal the production of more white blood cells, those white blood cells are going to be targeted specifically for the pathogen that the macrophage ingested and broke down. So instead of just ramping up all of the white blood cells and sending them out, they only send out the ones that are specifically capable of killing the specific pathogen that's been located. Okay? So that's what these lymphocytes do. Okay. The white blood cells have there's several different approaches, and again, we'll get into more detail later, but we've got the macrophages, which are kind of a one-size-fits-all type approach as far as, hey, you don't belong here, I'm going to kill you and digest you. And then you have the ones that are more specific then to destroy in larger numbers whatever that macrophage located and identified. And those are not one size fit all. Those are specifically created to fight off that pathogen. In the immune system, this is why if you come down with a virus, okay, it can take your immune system up to 10 days to get fully operational to fight that infection off completely. And that's because the white blood cells are being ramped up, right? We've got colony stimulating factor that is ramping up the production of the specific type of white blood cell that is going to go kill the infection that we are now experiencing. Again, that's why it can take time. When you have a bacterial pathogen, sometimes parasitic pathogen, you can be given antibiotics, which will speed up this process, because while your immune system's fighting, the antibiotic is actually also specifically targeting the bacteria and killing it. Viral infections, that's why they can last for up to 10 days, because it really takes, sometimes even longer. It really takes your immune system a while to get these guys out on the scene. Two types of lymphocytes. We have B cell lymphocytes and T cell. And we'll go into more of those later. And again, these guys are going to produce those antibodies we talked about, which fight I can't talk and write tonight. That's just all there is to it. Produces antibodies. Remember, antibodies are usually good, antigens are bad. These produce antibodies and fight specific infections. They hunt for those specific antigens. Okay. Leukocyte disorders. I'm going to go into these for a second. There's two examples that we'll use. There's something called severe combined immunodeficiency, or SCID. That's right there. This is going to prevent the maturation of T cells and B cells. So it prevents these main fighters, these main fighting types of leukocyte or lymphocytes, from developing. Because they don't mature and aren't there to fight off infections, guess what you can't do? You can't fight off infections. Okay, so what happens is there's an enzyme missing, and the enzyme that is not present is the one that's required for the T and B cells to mature. Those enzymes. So important to get those chemical reactions going. In this case, it's a chemical reaction that will produce the finished T and B cell. Okay. Treatment for this, you can either have regular injections of the enzyme so that it's being artificially introduced to the system to allow the T and B cells to mature, or you can get a bone marrow transplant. Bone marrow transplants are big deals because even if you don't have cancer, you have to undergo chemotherapy usually to kill the immune system and to kill all the white blood cells, at which point you can have new bone marrow transplanted that contains the correct enzyme so that when new blood cells are finally being produced by the new blood marrow or the bone marrow, it's going to have the enzyme that will let these mature. Okay. Leukemia. Leukemia is a cancer, which means that we're dealing with uncontrolled cell growth. The uncontrolled cell growth in this case is specifically found in the white blood cells. Cancer of white blood cells. So even though there's this uncontrolled cell growth, the white blood cells don't mature into anything. Now remember that this maturation process is extremely important in order to fight off the different pathogens that invade our bodies. And so it prevents the white blood cells from being effective. Ineffective. So there's lots of different types of leukemia, and most of the time these types are dependent on the type of white blood cell and the maturity, the stage of maturity of the cell. So in this, our page doesn't have it, but I will just relate to a case study. There was a 20-year-old that became unusually fatigued. The neck, armpits, and groin became swollen. When it says that, by the way, it's referring to the, oh shoot, why can't I think? It's referring to the lymph nodes. I got it out finally. So really it's saying that the lymph nodes in the neck, under the armpits, and in the groin have become swollen. And they hurt when they get swollen. It can happen when there's just an infection even, because you're increasing the amount of white blood cells. Puts pressure. Okay. In addition, bruises took a long time to heal. And when doctors performed a complete blood cell count, or CBC, the results showed that there was a high number of white blood cells. Depending again on the type and the numbers of white blood cells encountered, this can lead or point to leukemia. A lot of times there has to be a biopsy done of one of the swollen lymph nodes themselves to confirm leukemia. Because if you take a blood count and look at the white blood cells, when you're sick, you're going to see an increase in white blood cells because your body's fighting an infection. The type of white blood cells found in highest numbers in your blood can be an indicator of whether you're dealing with an allergen, a parasite, a bacteria. So that can help doctors kind of know which direction they need to go in order to look for the cause when it's not cancer. Okay, guys, hang in. Go over blood types. This is the second to last page. We're almost done. Blood types are kind of cool, but then honestly, as you can see, I think everything in biology is cool. They're all my favorite subjects. But blood types are determined by surface proteins on the red blood cells, okay? And there's different variations of those proteins. So everybody just doesn't have the same type of protein on their red blood cell, or we'd all have the same blood type. That should be a V, you guys. It keeps getting bigger and bigger. Variations of proteins on red blood cell surfaces. Yes, we're back to talking about red blood cells here. Okay. All right. When you're dealing with a blood transfusion, you're talking about transferring blood from one individual to another. And of course, in emergency medicine or in surgeries, blood transfusions are life-saving many times. But in order to make sure that the blood is compatible with the person that's receiving it, there have to be a couple of different factors that are matched. One of those factors has to be blood type. In other words, the person that's giving the blood has to have the same proteins on the surface of the blood cells as the person receiving it. They have to match. Because if they don't, an immune response occurs. And that immune response is actually going to make the red blood cells clump together. And of course, when blood cells clump together, you don't have blood flowing to parts in the body. And of course, you can also have a blood clot, which can kill you. So large amounts of blood that are transferred into an individual that's not the right blood type can be fatal. It's often fatal. In this case, clumping or coagulating. They'll start to stick together. Okay, so they're kind of giving an example of what these different types of antigens look like in these images over here. So a type A antigen, they're using circles. Type A antigen, in this case, is this sphere, right? Well, type B has got like a cone. Type AB blood has the cone and the sphere. And then we have type O, which if you notice has nothing, okay? And I'll get into that a little bit more in a second. When it comes to compatibility, then we're not only looking at these surface proteins, which we'll call collectively the ABO blood type, or sometimes ABO blood group. but also we're looking at the Rh factor. People are either Rh negative or Rh positive. That's to say positive negative is a little bit of a misnomer. That's not exactly how it works, but it makes it clear to deal with in everyday language. All right, ABO blood group. So we have these proteins, which are called glycoproteins. Okay, they're the ones that are on the surface, and they act as antigens. This allows foreign substances to be recognized by the immune system. So in this case, the antigens on the surface of blood cells allow the body to say, this is mine, this belongs to me, and this is my marker. Okay? That also means that foreign substances that don't belong to the body can be recognized, because they're not going to have the same markers. Okay. And again, the immune system contains antibodies that recognize non-self antigens. Okay. So to clarify this, if you have type A blood and then type B blood is introduced through a transfusion into your body, the type B blood acts as an antigen saying, I don't belong here, I'm not type A, I don't match, and that activates the immune system, which causes the clumping or coagulation response in blood when the wrong type is introduced into a receiver. Okay? So the immune system recognizes kind of what you can call non-self antigens. Okay, move this up. Let's talk about these different blood types and the combinations that can give us these different blood types. Make sure that's lined up for you. All right, so we have this chart down here. I'm not gonna, these bullet points here are meant to fill out type A, B, and O. I'm not gonna do that because first off, they're right there. Second, they're right there. A has A antigens, B has B antigens, AB has A and B antigens, O has no antigens, okay? So type A can donate to people who are either type A blood, so a match, or people who are AB. Since the AB blood type has both antigens on the surface, it recognizes both and it's comfortable with both. And so A can give to itself, to another A, or to an AB. However, as far as who it can receive blood from, you can only get blood from somebody that's either type A or O. A because they match, the antigens match. O because there aren't any antigens to fight. Okay? So type B, we're going to deal with the same thing. Donate to type B or type AB. But as far as who they can get it from, they can get it from type B or type O. Okay. People that have AB blood type, which is a rare blood type, these guys, they can only donate to people with AB blood because it's what they've got, right? They can't, these antigens can't be taken off the surface so that you only have type A antigen or type B antigen. However, they can receive from every flipping buddy. They're good with A or type B or type AB or type O. These guys are called universal receivers. Okay, universal receiver, bam, right there. Okay, they're the easiest type to give blood to, but it's not a super common blood type. Then we have type O. Type O can give to everybody because there's no antigens on the blood cell, and so there's no threat to anyone because they don't have anything to threaten with. Okay, so these guys can give to type O, to type A, to type B, and of course to type AB. These are your universal donors. Okay, because they can give to everyone. However, they can only get from other type O's. Kind of sucks. So an O can give to everybody. Blood donation centers and hospitals love type O blood because it can go anywhere. However, it can only be received from somebody else that is type O. And I haven't been talking about RH blood groups, but we're going to get into that now. Okay, last page, guys. RH blood group, here we go. So this is the other thing that has to be considered when giving blood to a patient. RH factor stands for rhesus factor. It was incorrectly named back in the day because the scientists that discovered it thought it had to do with something else. But anyway, RH factor. So the RH factor is either present or it's not. Okay? Either there or it's not. And this is also found on the surface of red blood cells. So we have these antigens and then we have an RH factor. So I'm going to write down kind of like a little chart thing. Kind of like what we did with blood to help. Okay, so how do I want to do this? So if you're RH plus positive, you can donate to another plus. Okay? But you can get it from positive or negative. Okay? So when we're dealing with RH blood groups, RH positive has, this is a flower, but it has antigens on the surface, whereas RH negative does not. Okay? So somebody that's RH positive can get an RH negative blood and they can be okay. However, this isn't the case with people that are RH negative. So negative can donate, as we know, to RH positive or RH negative, but, and it's a big but, it can only receive from somebody else who is RH negative. Okay? If somebody that's RH negative encounters blood that is RH positive, antibodies are made. Okay? Remember that antibodies are there to target antigens, and an RH positive blood cell has antigens on it, or that's how an RH negative blood cell looks at it. The immune system looks at the RH positive antigens and is like, and you don't belong here and we're going to kill you. This is an issue for a number of reasons. Obviously for the reason of the clotting factor and immune response that happens. Like you can be an O positive and you can be okay getting O positive or O negative blood, but if you're an O negative, you can only get O negative. It's really important that you only get the O negative. It's not just like, oh, you're both O, it'll be fine. No. If you have O negative, you can only get from O negative. Okay. So 85% of humans are Rh positive. Just this is kind of an FYI. 85% of people are Rh positive. So obviously that puts those that are an Rh negative in the minority here. Okay, so one of the other issues with Rh factor is in pregnancies. This wasn't actually discovered until the early 19th centuries when they kept having women dying at childbirth, but for no apparent reason that they could see. What would happen would be, well, you've got a couple of issues that can happen. It can be fatal to the baby, but it can also cause serious problems for mom. And so if mom is Rh negative, okay, but dad is Rh positive because of genetics, there's a possibility that the fetus is also Rh positive like dad. Okay, well, this is the problem. Because Rh negative individuals cannot encounter blood from an Rh positive individual, but because blood from mother to fetus mixes during pregnancy and often during childbirth, mom has suddenly been exposed to Rh positive blood. You following me? Okay, so this is a problem only if mom is Rh negative and fetus is Rh positive. Okay, that's when we encounter a problem. If mom's Rh positive, remember this isn't a big thing. Mom can be exposed to negative and be fine. The other way around doesn't work. So when mom is exposed to Rh positive blood from an Rh positive fetus, mom starts to make antibodies, right? She starts to make cells that are going to destroy this Rh factor when it's encountered again. A lot of times, the first pregnancy from a mom that's Rh negative, if that blood type has been undetected previously, will still result in a healthy birth for the mom and baby, okay? It's after this exposure and subsequent pregnancies that this can be a problem. If mom gets pregnant again and has another Rh positive baby, well, now mom's body recognizes the baby as an invader because of the antigen on the red blood cells that baby has. The body then starts to target the baby and can occur in fetal death. So today, this issue is prevented by something called RhoGAM. It's a immunoglobulin, and it's an injection given to Rh negative mothers within 72 hours after giving birth. Okay, and this prevents the formation of the antibody against the antigen found on an Rh positive fetus, in a Rh positive fetus. The thing is with this, it says 72 hours, but honestly, most of the time, if a mom is known to be Rh negative, and as long as she's getting prenatal care, she'll be tested, and so they'll find out blood type if she doesn't already know. Mom's going to get RhoGAM shots generally 3 times during pregnancy. One time during the pregnancy itself, and then I think they usually do one prior to labor and then one following birth. And again, this is to prevent the formation of antibodies so that if she gets pregnant again and it's an Rh positive baby again, we're not going to have this episode of mom's body attacking baby's body. And you do have to do the RhoGAM shot with every pregnancy if you're Rh negative. I guess I can put next pregnancy. Mom's antibodies to this Rh factor attack fetus. And this does lead to fetal death, miscarriage. Sometimes miscarriage can take place if a mom doesn't know her Rh factor, if she hasn't been tested. Sometimes this can happen, and it seems like spontaneous miscarriage, because it is, I guess, and yet in this case the spontaneous part is because of the Rh factor. All right, we talked about RhoGAM and that this prevents formation of antibodies against the positive Rh factor. antibodies in mom. Okay. All right. So your question of the day in this that we'll go over briefly, can your immune system target cancer? The short answer to that is yes. It can, because cells that are damaged or not functioning correctly or have a damaged part often give off a chemical signal that there is something wrong with them. In this case, macrophages are usually what will come along and ingest them and destroy them, or the cell itself will signal the process of apoptosis, which is cell death, to take itself out and prevent it from replicating. However, while the immune system does have the ability to target these types of cancer cells that announce that they're cancer cells, we have a lot more types of cancer cells that evade detection by the immune system. So yes, it can and does on occasion, but we now have more types of cancer that know how to fly under the radar. That's because most of the time, if the cell is not providing like the signal of, hey, come kill me, the body just keeps recognizing the cell as belonging to the body. You know, it's like, this is mine. Why would I kill it? It belongs to me. So to counteract that, there's a type of cancer technology that's being developed where T cell lymphocytes are being designed in a laboratory to target cancer cells, but not, right now these are not effective against some of the more common cancers like breast cancer. Which is funny because this article is talking about how it did. So I gotta look up on that because I think some of my information may be older than what's printed here, vice versa. Obviously breast cancer is one of the more studied cancers because of how many people it impacts. So this would definitely be a type of immunotherapy that they would want to develop. Sorry, I'm just trying to pull up some more information on my own so I can read this a little bit more for you and see if I can find out the answer to that, because I don't want to leave it where it's not right. Okay, so here's one that says that yes, this actually pulls up this article. This article does talk about this type of therapy being able to effectively kill metastatic breast cancer. Metastatic means that it's moved to other parts of the body, which is what makes it so deadly. And so they are making advances in being able to take out that type of cancer as well. But essentially you have these T cells that have been developed to target a specific type of cancer. And it doesn't affect the other cells. It's just looking for the cancer cells and the specific cancer cells that it's been created to identify. These have billions of copies made of them in the lab. And then those are injected into the patient and sent out as like this, army to go identify and destroy every single invader they can find. And the invader in this case is cancer. Okay. So guys, made it through. You did good. I tried to keep these short compared to the fact that if we'd done it in class, it would have taken longer. It's shorter. But you'll have to give me your feedback. Let me know what you think of them. All right. I'll talk to you later. Bye.